This is the third example for trying to determine intervals on which a function is concave up or down, and do we have any points of inflection. In this one, we have a rational function, a polynomial divided by a polynomial. Now, it's important to note that if you look in the denominator of this polynomial, there are two values that will actually make the denominator 0. So if I said x squared minus 4 equal to 0 in factor, it's x plus 2 times x minus 2. So x equals negative 2 and 2 would make this function undefined. So these are important to note. I'm not going to include them in my points of inflection because the function is not defined there, but I'd certainly want to consider them when I'm writing my intervals. So I'm going to start with the first derivative. So f prime of x equals, and I'm going to use the quotient rule. So it's the bottom function, the denominator, times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So to clean up my numerator, I'm just going to distribute and then combine like terms. So this will be a 2x cubed minus 8x. Then I'll distribute a negative 2x. So negative 2x cubed minus 2x. These cancel out, and I'm left with a negative 10x over x squared minus 4 squared. And that is my first derivative. So I need my second derivative, and again I'm going to use the quotient rule. So f double prime of x equals my denominator times the derivative of my numerator, negative 10, minus my numerator, so minus a negative makes it a plus 10x, times the derivative of my denominator. That's the chain rule. I have a u squared, so 2 times my u to the first, times the derivative of the inside function, a 2x, divided by my denominator squared. So it's a squared squared, so it's to the fourth power. If I look, you can see that there's at least one x squared minus 4 in each one of these, so I'm going to cancel it out, and I will be left with a negative 10 times, and I'll have one x squared minus 4 left, plus I have 10x times 2 is 20x, times the 2x is 40x squared. That x squared minus 4 cancels out, so I'm only working with my numerator here. This would turn into a third power for the denominator. I'll go ahead and write that for this step. So x squared minus 4 to the third. Then I'm going to clean up my numerator by distributing my negative 10. So negative 10x squared plus 40 plus a 40x squared. Combining like terms, I have a 30x squared plus 40 in my numerator. I can factor out a 10 if I like, so you could if you want. I'm actually just going to leave it. So my second derivative, I'm going to leave it as a 30x squared plus 40 over x squared minus 4 cubed. Now if I look at my numerator to see where it's actually equal to 0, I can tell that it's never going to be equal to 0 because this is definitely positive. The least the least x squared again could be is 0, but I'm still adding 40, so this is greater than 0. I already know the values that would make my denominator equal to 0, so they are x equals negative 2 and 2. Cubing it doesn't change that. 0 cubed is 0. So I don't actually have any possible points of inflection, but I can still determine my intervals for concavity. So the values I need to consider are negative 2 and 2 because I have some asymptotes there. And I'm checking the sign of my second derivative. So I know my numerator is always going to be greater than 0, so I'm really just checking my denominator. If I pick like a negative 10 and square it, I'm going to get 100 minus 4 is positive. A positive cubed is a positive, and my function is concave up in this interval. If I take 0, 0 squared is 0, minus 4 is negative, and negative cubed is negative. My function will be concave down in this interval. I take a number to the right of 2, like 10. I'm going to get the same thing that I did for negative 10 because it's squared, so concave up in that interval. So my function is concave up on negative infinity to negative 2 and from 2 to infinity. And I know that because f double prime of x is greater than 0. It's concave down on negative 2 to 2. And I know that because f double prime of x is less than 0. And I have no points of inflection. Even though the signs changed, my original function was undefined at both of these values, so they can't possibly be points of inflection. And that is the third example.